morning, students, again. So, yesterday we have studied two LAQs from wave chapter. One is stationary wave in stretched string, loss of transverse wave on the stretched string. Second one is formation of stationary wave in open pipe and different harmonics. Very similar to that open pipe. There is one more question is there from the same wave chapter. That is formation of stationary wave in an closed pipe and explain the different modes of vibration of closed pipe that we will see now. So I will explain what was the formation of stationary wave in a closed pipe and what are the different harmonics will form in closed pipe. We'll see, and after that we'll see also some few like that every long answer type of question there is a short like one numerical question also will attach it to that, which carries 2 marks. The remaining question is carries 6 marks. The last part of the numerical part will carry the 2 marks. So 6 plus 2 pattern will be present. So for that, I will explain few of them important numerical questions also for this chapter. Okay. So we'll start with that is third LAQ, which is from the same wave chapter only. Waves LAQ third one. So that is formation of stationary wave in an closed pipe and explain modes of or different modes of vibrations in closed pipe. Okay. Formation of stationary wave in a closed pipe and explain the different modes of vibrations of closed pipe. That is what question. Now for this, what we have to know, first of all, what is closed pipe? We need to write. What is closed pipe? Yesterday I said what is open pipe, right? First, so we have to start with our answer with what is closed pipe. Then, so we need to explain how the formation of stationary wave in closed pipe. The third one is different modes of vibration we need to explain, correct? So like that, step by step, we need to write in the answer sheet. So first one will say what is closed pipe. Closed pipe. What is closed pipe? Simple. Closed pipe is a simple a tube, cylindrical tube, open at one end and closed at other end. Open at one end and closed at other end. Simple. A tube open at one end and closed at other end. Open at one end and closed at other end. We call it as it is a closed pipe. Okay. So that is simple. We can say a cylindrical tube open at one end and closed at other end. This end is opened and this end is closed. So open at one end and closed at other end. We call it as closed pipe. We call again it is open at one end. So that inside the pipe again is air is enclosed. So this is also we call air column only, but closed at one end. So as usually, for example, as usually just like in stationary wave formed in open pipe, Same procedure it will follow in closed pipe also, but only the difference is suppose in a vibrating tuning fork, if you keep here, vibrating tuning fork you keep near to the open end of the pipe, then this vibration will pass into the pipe, So that is considered as incident wave. So these are passed into the pipe and they are strike on closed end. They strike on closed end and reflected from the closed end. This reflected wave from closed end and the incident wave both are superimposed to each other and forms a resultant stationary wave. So what we have to write? Simple. Whenever a wave is passed through the closed pipe and it is get reflected from the closed end, and the reflected wave and incident wave are superimposed to each other and forms a resultant wave called stationary wave in a closed pipe. And we know that closed end means it is not allowed to vibrate freely. So at the closed end, the displacement of the particles, vibration displacement of the particle is minimum or zero, we can say. And the open end displacement of the particle is maximum. So that we can say closed end node will form always, open end antinode will form. So in that way, there is a stationary wave will be formed inside the closed pipe. So that based on that, open end means antinode will form, closed end means node will form. So like this, stationary wave in closed pipe will form. So here node will form and here node, and here antinode, here also antinode. Like this, the stationary wave in a closed pipe will be formed. Okay. So we need to write this is an antinode, this is an antinode, this is node, and this is also node. And closed end always node will form, open end always antinode will form. Okay. So how to write? When a wave passed through closed pipe or closed pipe, it get reflected from closed end. The incident wave and the reflected wave are superimposed to each other and forms stationary wave in closed pipe as shown. As we shown there, the closed pipe, we get the stationary wave inside the closed pipe. Along with closed end, we get node, and open end will get antinode. Is it clear? So this is way the formation of stationary wave in a closed pipe. Then again, the wave is going inside the closed pipe means it is a wave velocity will be present v and frequency f and wavelength lambda. So as we consider it as the length of the tube is as usual, it is considered as L. L is the length of the tube, and we say the speed of wave, that is V, that is equal to frequency into wavelength. And from this frequency of vibration of a stationary wave in a closed pipe, I can write F is equal to V by lambda. V by lambda. Now we'll see formation of stationary wave and closed pipe is completed, this much. And explain the different modes of vibration in a closed pipe. That we need to explain now. So different modes of vibration means same. That is harmonics will form. Different types of harmonics will form. Yesterday we have seen that all types of harmonics formed in open pipe. Even we got, and also odd number also we got. But here what type of harmonics will get? Whether only even will get, or only odd number will get, or all will get again. We'll see. Or any difference between fundamental frequency or minimum frequency in open and closed pipe. We'll see little bit different will be present, obviously, because here one end is open and there both the ends is open. Open pipe means both the ends are open. Closed pipe means one end is open. So definitely there will be some difference will be there. So we'll discuss now what are the different modes of vibration in a closed pipe. Okay. So this side I will rub it and I will explain the different modes of vibration. Yeah. So first mode or fundamental mode we call. Fundamental mode or first mode. What is fundamental mode means? Minimum, the closed pipe which is vibrate with the minimum frequency or minimum possible stationary wave loops. What is that? We'll see now. Fundamental mode. See, this is a closed pipe with of length L. Okay. And we know very well here compulsory node should form and here compulsory antinode will form. So the minimum to minimum possible case is here node or here antinode, and the minimum separation between node and antinode we know that lambda by 4. Lambda by 4, because node to node is lambda by 2, antinode to antinode is lambda by 2, but node to antinode is lambda by 4, 1/4 of wavelength. So for that, the first fundamental mode of vibration will form like this. So here antinode, here node. Okay. Then we know that the entire length of the tube is only the antinode and node to distance. The length of the tube is indirectly antinode to node distance only. So from this I can say L is equal to antinode to node, that is lambda by 4. And from this lambda I can write 4L. And from that formula, the frequency I can write it as V by, in place of lambda should write 4L. And this is we call fundamental mode of frequency, or correspondingly we can call fundamental frequency. Got it? समझ में आया? Fundamental frequency. Or this is fundamental frequency, or also we call first harmonic. First harmonic. So let us consider it as F1. This can be written as 1 into F. First harmonic. Okay, 1 into F. Now coming to the next mode of vibration. What is next mode of vibration means? Already the minimum mode at the closed end node and antinode will at open ended form is completed. So the next mode of vibration, you see, what is next mode of vibration means? See here, length of the tube as usual is same length L only, but the second mode of vibration here node or antinode is completed. So apart from this, again node, antinode will come, plus one complete loop will come. Second possibility, one complete loop. That means like this. Like this it will come. That means here node, here antinode, that is fixed. And in between here also one more antinode we got, and here one node we got. That is complete loop we got. 1.5 loop we can say. Here half loop, there 1.5 loop. Again, we can say from here, the length of the tube can be calculated by, you see here, anti-node to node lambda by 4 and node to node is a lambda by 2. That means I can write here lambda by 4 plus node to node is lambda by 2. And if you simplify this one is LCM will be 4 here. 1 plus 2, it will come it as 3 lambda by 4. Implies lambda can be written as 4L by 3. Now frequency will write frequency F is equal to V by lambda, that is equal to V by lambda place I write 4L by 3, that will 3 come up. And from this you see V by 4L is a fundamental frequency. V by 4L is a fundamental frequency. And we are getting here multiple with the 3. Multiple with the 3. Initially we got multiply with 1. But here again next immediately we get multiple with the 3 we got. That means 3V by 4L. I can write it as 3 times of fundamental frequency. That means we can write this is F3 and this is 3F. That means F3 is equal to 3 into F. This is third harmonic we call. Third harmonic. That means initially one we got, next second one is missed, and next we got third one directly. So first after third we got third harmonic we got. So we can write here starting as third mode vibration or third harmonic. Clear now? Next mode of vibration we'll see whether we'll get a fourth one will get or fifth one will get. Well, let us one more we'll see and check it. So next mode of vibration. So same the length of the tube as usually L. Okay. Now we will get here 1.5 loop we got, right? So next time we'll get 2.5 loops. 2.5 loops. Like this. 2.5 loops we'll get. This is anti-node. This is node, this is anti-node, and in between this is also anti-node, anti-node, node, node. This is length of the tube. Then as usually the length can be calculated by this is node to anti-node. Anti-node to node is lambda by 4 plus a lambda by 2, a be lambda by 2. Lambda by 2 plus lambda by 2. It becomes 4 is a LCM, 1 plus 2 plus 2, it becomes 5. So we can write it as 5 lambda by 4, that is L. And from this lambda can be written as 4L by 5. And the frequency can be expressed as V by lambda and V by 4L by 5. Again, we see V by 4L is a fundamental frequency. V by 4L is a fundamental frequency, but we are getting the multiple with the 5. Again, the fourth one is missed here. After third, we are getting it as 5 only. Fourth one is missed. So that means I can write it as fifth frequency, or we can write fifth harmonic. And this is Fy, that is 5 into F. So call it as fifth harmonic. So from this, what we can understand means we are getting 1, 3, 5. So next, if you calculate, definitely 7 will get, 9 will get, 11 will get. That means odd numbers only we are getting, not even number. That means even number of harmonics are missing. Even number of harmonics are missing. Only odd number of harmonics are forming. That means in a closed pipe, only odd number harmonics are formed and ratio of frequencies is 1:3:5:7 and so on. Only odd number ratio. Only odd number ratio. Is it clear? So this is the third question, that is formation of stationary wave in closed pipe. Simple. First we need to write what is closed pipe. The pipe, a tube is open at one end and closed at other end is called open closed pipe. And whenever wave is passed through a closed pipe, it is get reflected from rigid end. And this reflected wave and incident wave are superimposed to each other and forms a stationary wave inside it. Speed is equal to frequency into wavelength, we should write. And from that, frequency is equal to V by lambda. The different modes of vibration. So first of all, fundamental mode of vibration. In this one, closed end, we know I told that rigid end or closed end. Minimum displacement, that is node will form. Free end or open end. Maximum displacement or antinode will form. So minimum case is here node, here antinode. So the length is can be lambda by 4. Lambda is equal to 4L. From this fundamental frequency, we got 4 V by 4L. And here, next mode we got 1.5 loop width. So we calculated that is 3 times of V by 4L. And the next is 2.5 loop, that is 4 times of V by 4L. Like this, we are getting 1, 3, 5. That is odd harmonics only we are getting. Clear now? So this is where we need to present on the answer sheet. Okay, step by step. This is the third LAQ, and from this wave chapter, this 3 are you perfect? Definitely you can answer one question. Clear? So let us receive some numerical questions from this chapter. Along with this theoretical question, there will be one numerical question will be attached to this. So what are the numerical questions? Some model questions are already which is previous yearly they present in this question paper. We'll see now. Okay. Clear? Numerical problems. So first question we see, which is recently in your exam, March 2023 question paper. What is the numerical question? We'll see now. See the question which is asked in the recent exam, that is, how are stationary wave formed in a closed pipe? And explain the various modes of vibration and obtain the relation between the frequencies. How are stationary wave formed in closed pipe? Just now I explained how is stationary wave formed in closed pipe. And explain the different modes of vibration. Just now we see 1, 3, 5 mode of vibration, odd number of vibration. And obtain the relation for their frequencies. That is 1:3:5:7. Relation is 1:3, 1:3:5:7 frequencies ratio we have. So that is what. And along with one numerical question was given. What is that? We'll see now. Question is, a closed organ pipe 70 centimeter long is sounded. A closed organ pipe, simple cylindrical pipe only. Closed organ pipe 70 centimeter long is sounded. If the velocity of sound is, 330 meter per second, 330 meter per second, what is the fundamental frequency of vibration of the air column. What is the fundamental frequency of vibration of the air column? This is a question. A closed argon pipe 70 centimeter long is sounded. If the velocity of sound is 330 meter per second, what is the fundamental frequency of vibration of the air column? So which organ pipe or which closed pipe is given? Closed pipe is given. The length of the pipe is given how much? 70 centimeter. And speed of wave is given 330 meter per second. And they are asking what is the least or fundamental mode of vibration frequency they are asking. And just now we have got the equation. The fundamental frequency we got. Fundamental frequency of closed pipe. And we know that is F, that is equal to V by 4L. V by 4L. So this can be expressed as we know F is equal to V, speed of sound, 330 meter per second. Here we have value, and L, length of the tube, that is 70 centimeter, here also given. So L is given, V is given. Just we'll substitute in the formula and get simplify. We'll get the answer. That is V 330 and 4 into L. L is 70 centimeter they've given, but we need to convert into SI unit, that is meter. So 70 centimeter convert into meter means multiply with 10 to the power of minus 2. So from this minus 2 will go up, and from this 0 and 0 cancel out. So we'll get 33 into 10 to the power of 2 by 4 into 7. Or I can write here 4 into 7 only as usually. So from this we can write 4 ones are 4, 8s are 32. 4 8s are 32 and 1 will left, and that is 1, it can be written as 2 pi. 8.25. Then 8.25 by 7. 8.25 by 7. 8.25 by 7 again if you want to calculate, or otherwise I can write 8.25 into 100. 825 by 7. 825 by 7. So if I cancel with the 7 table, so can I say 7 10s are 70 only? But 7 11s are 77. 7 12 means it will go. Beyond it will go. Right? So 84 it will come. Right? So 82 only we have. So I can cancel with 7 1s are 7. 11s are. It will become 77 left with the 5. 55 is there. So 55 means 7 8s are 56, but 7 only we need to go. So 7. 49. So 55 is there, 49 we got. So it is 66 is left. So we can write approximately 0.8. So now finally the answer is 117.8 hertz. 117.8 hertz. This is the fundamental frequency of the closed pipe as of given data. Clear now? Simple. Length is given, speed of sound is given, formula we know, fundamental frequency V by 4L, and substitute and simplify 117.8 and hertz. Clear now? Similarly, one more question we'll see. Similar to that, a pipe of 30 centimeter long, open at both the ends, means open pipe. Find fundamental frequency if speed of sound is 330 meter per second. If speed of sound is 330 meter per second. So 330 meter per second. So pipe is open is given. Fundamental frequency we need to find. So from this length is given as 30 centimeter, or we can write 30 into 10 to the power of minus 2 meter. And speed of sound is given 330 meter per second. And fundamental frequency formula for open pipe is V by 12. V by 12. So V is given simple 330 by 2 into L is 30 into 10 to the power of minus 2. So from this 0 cancel, 3 ones are 311 will be get, and it 10 to the power of minus 2 it will go up, means 11 into 10 to the power of 2 will get by 2. And this is become 1100 and by 2. So finally answer 1100 by 2 will be 550 hertz. 550 hertz. This is answer. Clear? So like this basic formula of fundamental frequency, they will give the data and just substitute in that. That's it. V by 2L for open pipe, T by 4L for closed pipe, and root of 1 by 2L root over T by mu is a stretched string. These three formulas only the question will ask. Mainly this open pipe or closed pipe they will ask. This is the way we need to do. Clear now? Okay. So now we'll see from current electricity chapter, one more long answer weightage chapter from current electricity chapter. So important question it is, that is state the laws of Kirchhoff or Kirchhoff law. State Kirchhoff law of current circuits and apply this to obtain the balancing condition for Wheatstone bridge. Correct? So what is that? We'll see now that question. Okay. Current electricity LAQ. Okay. So what is that LAQ? See the what exactly they are asking. So that is state question I'm writing here. State Kirchhoff laws. Kirchhoff laws of electrical network. And using this, using these laws, deduce the condition for balance in a Wheatstone bridge. Wheatstone bridge. The same thing can be, they can ask in different way, derive the balancing condition of Wheatstone bridge, or apply the Kirchhoff laws to Wheatstone bridge and derive the condition for Wheatstone bridge. Okay. So anything is asking balancing condition of Wheatstone bridge or state laws of Kirchhoff laws. So answer is remains same on different wording is there, but the answer is remains same. We'll see what is that explanation. Look here. Simple. What the question is given, state Kirchhoff laws of electrical network. Using these laws, deduce the condition for balance in a Wheatstone bridge. So first, what are the Kirchhoff laws of electrical network? We'll see. And we'll try to apply this for Wheatstone bridge and get the balancing condition for that. Okay. Right. First law. First Kirchhoff law, or this is also called junction law. Junction law. What is junction law means? In an electrical circuit, at any junction, junction means it is a point where two or more ways are meeting. Two or more ways are meeting, right? So in this, in terms of electrical network, what are the two or more ways means? It is a current flow direction. So junction law, what it's saying means, the algebraic sum of currents at the junction is 0, or we can say the sum of the current flowing towards the junction will be equal to the sum of the current flowing away from the junction. That means diagrammatically, if I want to draw it, this is a junction O. Then this is a two currents which are flowing towards the junction, that is I1 and I2. Two currents are flowing towards the O. And from this, there are three currents flowing away from the junction, like I3, I4, I5. The sum of the current, that is total current of I1 and I2, which is coming towards the junction O, which is moving away from the junction, that is I3, I4, I5, is equal numerically. That is, sum of the current towards the junction is equal to sum of the current flowing away from the junction. That means at the junction, no current will remains. No current will be remain. Jitna aa raha hai, utna hi jayega. That maybe it's coming as a two ways, but moving as a three or four ways, or only one way, not about. But how much current is coming towards the junction, that much of current will move away from the junction, and no current will stay at a junction. So that is only we can write here, sum of currents flowing towards junction is equal to sum of current flowing away from junction. That is, I1 plus I2 will be equal to I3 plus I4 plus I5. Sum of the current flowing towards the junction is equal to sum of the current flowing away from the junction. Or I can say implies sigma I, sum of the all the current will be 0 at junction. मतलब दो करंट स्टेट एट जंक्शन, जितना आ रहा है उतना ही जा रहा है. सो जंक्शन के पास कितना करंट है, मतलब जीरो करंट, नो करंट इज देयर एट द जंक्शन. करेक्ट. सो दैट इज सिग्मा आई इक्वल टू 0. दिस इज फर्स्ट लॉ. सिमिलरली सेकेंड लॉ. फर्स्ट क्लास समझ में आया? सिंपल. द करंट विच आर फ्लोइंग टुवर्ड्स जंक्शन विल बी इक्वल टू द करंट फ्लोइंग अवे फ्रॉम द जंक्शन, और टोटल करंट एट द जंक्शन विल बी 0. Second law, or it is also called voltage law or loop law. Voltage or Loop law. What is mean by loop here? Loop means closed path. Closed path. So where we have started and it goes on different parts and come back to same point. Closed one. Closed path, we call it as loop. So what is voltage or loop law means? From this statement, in any closed loop or any closed path, in any closed network, electrical network or closed path, the sum of voltage or potential difference, you can write. Potential difference is 0. That is, sigma V will be 0. Sigma V will be 0. Clear? Sigma V will be 0. For example, for simple electrical circuit you want to draw like this, you can draw it. There is a battery here and there is a simple resistor is there, and here one more resistor is there, and I can say this is as R1, this is as a R2. Current flows like this. This is the battery voltage V, EMF E. Let us consider R1. Current is like this is flowing. For this, we need to know that algebraic sum of a total voltage is 0 means when we are moving in a closed loop. So first of all, we need to define what is our loop, what direction we are considering it is a closed loop. So first of all, we need to consider one closed loop. Then in this closed loop, when we are moving, if we are moves from high potential to low potential, higher से lower जा रहा है, तो वो potential difference negative रहेगा. मतलब I से low आ रहा है, negative रहेगा. नहीं, low से high जा रहा है, low से high जा रहा है, so that will be a positive. So in the loop, when you are going from higher to lower, it is considered as a potential difference negative. Lower to higher, the potential difference considered as a positive. Correct? So if you want, I can write here, potential difference is positive for high potential, low potential to high potential is moving. And potential difference is negative for high potential to low potential moving. Okay. So from this, in this example, I can write, we are starting with, let us say, consider this is A, this is B, this is C, this is D. That means I consider a loop as A, B, C, D. Loop is A, B, C, D. From this loop, I can say start with A. Start with A. When you are going in a loop, higher to lower is negative, lower to higher is positive. And we know that when you are going in a loop, if is there any resistor is there and through which current is flowing. Normally current flows from high potential to low potential. And there is a battery is there. Battery means, you know, long line represent high potential point, short line represent low potential point. So that means first condition, we need to choose a loop. Second condition, based on the direction of current, we need to mark the high potential, low potential across resistor and in battery also. So for that, in this one, I mark the high potential, low potential. Current is flowing like this. So current flowing in this direction means this should be plus, this should be minus. And it is coming like this, current flowing like this direction. That means this is plus, this is minus. But it is a battery, short line represent minus, long line represent plus. Plus represent high potential, minus represent lower potential. Now coming to the point, when you're going from A to B, we are not going through any resistor, right? Again, B to C, one resistor is there and current I is flowing here. And that too, it is flowing from I to low. The potential difference across resistor is I into R, and it is in the direction of current or high to low is going. So we consider it as minus I into R2. Now coming to C to D, no resistor is there, but D to A, there is a one resistor is there. And log with current is flowing high to low, that is again minus I into R1 And again from lower to higher in battery is moving. So lower to higher means it become plus, that is EMF E will be 0. So our loop is like this is there. Correct? So this is loop law application, minus IR2 minus IR1 plus E is equal to 0. First law of junction law or second law is loop law. These are what you call statement of two laws of Kirchhoff's. Two laws of Kirchhoff. State Kirchhoff laws of electrical network. This is first law and that is second law. Mainly you need to write first law, current flowing toward junction is equal to away from the junction. And sum of the closed path, in any closed path, the sum of the potential difference is 0. But just one example here and one example here for this. Is it clear? Simple. Sum of the current flowing toward the junction is equal to sum of the current flowing away from the junction. Total potential difference in any closed path is 0. These are the two laws of Kirchhoff. Now we'll apply this Kirchhoff laws, two laws to a Wheatstone bridge. Wheatstone bridge is it is simple. A group of 5 resistor forms as a 4 arms of the square or rectangle, we can say, right? So that we'll see now what is Wheatstone bridge and how we'll apply this laws to Wheatstone bridge and get the balancing condition. Okay, is that laws are clear? Right. Yeah. So just now we explained the laws of Kirchhoff's. So those two laws will apply to Wheatstone bridge and get the balancing condition. See what is that? Wheatstone bridge is simple. It's a combination of one battery along with 5 group of resistors connected as 4 arms of the rectangle, and 4 arms or 4 resistor will be present, and diagonal will have one of the diagonal will have 5th resistor, and that is called galvanometer resistor we call. So circuit diagram, if you see, we have a circuit diagram like this. Okay, here one resistor will be present, here one more resistor will be present, here one more, and here one more, and we name this is P, Q, R, S. 4 arms of the rectangular square you can consider PQRS, and here the diagonal of that one one more resistor will be present, that is galvanometer resistor. Okay, so now between these two ends, so which is named as A, B, between A and B terminals we will connect a battery with the EMF, and this remaining, this is C and D at terms. So this we connected with a battery of potential difference or EMF E. Okay, this is Wheatstone bridge. Now coming to the point, so from the first law of junction, current flows toward the junction is equal to away from the junction, right? We'll split up the current in the Wheatstone bridge diagram. So assume that there is a current I is coming here, like I current is coming, and split up current here like I1 and I2. From R resistor, I2 current is going, and I1 resistor from P resistance, I1 current is flowing towards the C and towards the D. And from this one, I1 is current coming at the junction of C. That means we can write from junction law. Junction law. At A, from junction law, at A junction, if you apply, I can write I is equal to, I is flowing toward the junction A and I1, I2 are flowing away from the junction A. That means at A, I can write I is equal to I1 plus I2. I1 is flowing towards C, I2 is flowing towards D. Now coming to the point at C, again C is a one more junction. From the C, there is a current is coming, I1 current is coming. And this I1 current again will split up one current flows towards the D through a galvanometer, and one more current is flows towards the B through a resistor Q. So I consider this is I3 and this consider IG galvanometer represent. So again I can write it as at C junction I can write I1 is equal to IG plus I3. Correct? Now coming to the point again, I2 is coming towards the junction D and even IG is coming towards the junction D. That means current flows towards the junction, that is one more IG and I2 which are coming towards the junction. Sum of these two current should be equal to, and one current is flowing towards the or away from the D, that is I consider it as I4 and it is going towards B. That means at D I can write IG plus I2 will be equal to I4. Now the finally from Q there is a current Q3 is I3 is coming towards the B, and from S there is a I4 current is coming towards the B, and the output current again it will go I, because I current is entering here, I current will be leave out from here. So I can write at B finally I3 plus I4 become I only. That is from the battery current I is leave and it is passing across the network and finally coming to negative terminal of the battery again, same amount of current will come like this. So these are 4 laws of junction. We have got it. Now we'll apply the Kirchhoff's second law, that is voltage law will apply. So what is voltage law means? First law will apply, that is something like this. We'll see A, C, D, A. A, C, D, A is one loop. I will take loop 1. And this is something like loop 2. Okay. Loop 1, loop 2. First, from loop law. So for the loop, what you take? A, C, D, A. A, C, D, A. A, C, D, A. I'm taking a loop. A, C, D, A. So start with A and go towards C and towards D, towards again A. That is a loop. Now just now I told second law of voltage of Kirchhoff. I said sum of the potential difference in any closed path 0, or high potential to low potential means negative, low potential to high potential means positive. Now coming to the point here, you see current flows higher to lower, plus minus. Current flows higher to lower, plus minus. Current flows higher to lower. This is plus, this is minus. Just marking so that we can easily come to know that whether negative or positive. Now coming to the point, A to C. You start with A, right? A to C we are going potential difference. I to low we are going plus to minus. That means I1 into P, it is a minus. And C to D, again it is coming from higher to low.